All right. Yep, there come some people. Fair enough. So I assume people who are here got the memo that we're starting at 3 instead of 1 because of the CCDC today.
Didn't get the room number. Saw the time change.
Yeah, well, last time I moved up here, I think, too. We'll just leave it up here because they're always needing that room down there longer for the competitions. All right. Anyway, so the topic today is 64-bit exploitation, which is good stuff. And I don't nuts. Wait a minute now. This is not right. All right, let me find out what the problem is. That would probably be this. Yes. No signal. That is probably because somebody bent this. All right. Let's see. There may be some way to feed a signal in more directly. Instead of going through this stinking camera. And perhaps there is not. All right. Aha, I think there is. HDMI 1 and 2 over here. Over there, let's try this. HDMI 1. And now, that perhaps. Aha. Okay, good. That'll get us through the day. So, all right. So let's talk about 64-bit processors, which is what almost everybody has these days. The problem with 32-bit processors is not so much that they're slower, although in principle they'd be slower, processing less bits per instruction, but that the address space is too small. 2 to the 32 is only 4 billion. This is the problem with IP version 4 on the internet, and this is the fundamental problem with 32-bit processors. You can't effectively address more than 4 gigabytes of space. And that's not enough RAM for modern machines. So 64 bits is the answer, and that's the game. So now you use R in front of the address names, in front of the register names. It all started with only one register called the accumulator A, which was 8 bits. And then you had AX, I think, and then EAX for 32-bit. And now we just switched to R for the long ones. So there's the game. All right. You now have a lot more registers too. You have 16 registers. This means a lot of things are going to get simpler because you can just use registers to move data in and out of functions, whereas before you'd have to push everything on the stack and pop it off the stack all the time. So you can, as in 32-bit registers, you can refer to parts of a register. Now you can refer to the 64 bits or the lower 32 or the lower 16 or the lower 8. So you
still have the AX?
Yes, you still have the AX, and it means the lower 32 bits of the AX register. Okay. So you can use 8, 16, or 32 bits per instruction if you want to. And as we'll see, there are cases where the 64-bit version you want does not exist. Another fun fact is that nobody actually uses all 64 bits for addressing. That would seem to be silly, but the point is that is far more memory than anybody could ever afford to buy right now anyway, so nobody cares. So they really only support 48 bits or something like that for the addressing. So Windows, and of course, as you get used to if you study Windows, it is always much more complicated than you think at first. So Windows 8, for example, in principle uses 48 bits, so it could address up to 256 terabytes of RAM, but there are other limitations. And if you look at the different versions of Windows, you'll see none of them go higher than 24 terabytes of physical RAM you can actually use. And the actual amount of RAM you can refer to within one process is also smaller, and this has been true in all of the earlier versions of Windows too. There are many different limitations at different levels. Anyway, so here's another strange thing. The RAM that you can use is split into 2 chunks. The operating system uses the top half, and the user programs use the lower half, all of their addresses starting with a whole bunch of zeros. It is not one contiguous block of memory. There is a dead zone in the middle of the RAM space that you cannot use. Any attempt to use those addresses will result in an exception because they are not available. Now, if we actually had 64-bit addressing, it would all be available, but it would still be split into two halves. Yeah?
What is that unavailable? Is that for the kernel?
No, the unavailable part cannot be addressed because you are not implementing those bits for the addresses. You are not allowed to use certain bits in the address space. And instead of just not using the first 16 bits or something, which would put everything down in the low space, for some reason they use the first bit and then skip a bunch after that. So the first bit is either 1 or 0. It puts you either in the top half or the lower half, and the next like 15 or bits are not usable or something. They always have to be 0. And that has this result of putting you in the top range or the bottom range. This probably made sense to somebody who designed this stuff. It sure does look kind of funny from this point of view.
It doesn't look sequential.
It's not. It's not. And this is the kind of thing that is pretty messed up. If you look at, say, Windows, 32-bit Windows, I think it was FAT32, and Windows had the rule that you could address up to 4 gigabytes of RAM, but an individual file couldn't be bigger than 2 gigabytes or something, because there was a similar issue there. Anyway, so you don't use int80, you use Syscall, which doesn't matter that much, but the most important thing for us to see is, unlike int80, you never use the stack. The number of the system call is passed in the register RIX, and all the rest of the registers are used for the orders. You can have a maximum of 6 parameters, and they just use these things, RDI, RSI, RDX. You're going to see more of this. This actually is another reason why processing gets faster. A lot of things have to be put in registers, which are much faster than RAM. It's just that you couldn't do that in a 32-bit processor because there are not enough registers available to force you to use registers for certain purposes. So you can go online and see a Linux Syscall table. It's at this link, and you'll see the write-up of these things. So here is a Syscall. Syscall 0 will read, Syscall 1 will write, and off you go. And you can get the details of what's going on here. So we did this stuff in raw assembler on 32, and we're going to do it on 64 to see the assembler. So there's a link here that takes you to all the details of all the registers and so on. And by the way, there are more registers than what I told you about. There are XMM registers, whatever those are, and floating point registers. There's a lot of registers, and there's analogies to those in the 32-bit processors too. These extra registers that aren't used that often.
So 80-bit floating point?
That's what it says. I don't really know enough about floating point. But yeah, I guess so. Floating point has to be longer. And all right. And so you got very similar opcodes. You got move and compare and rotate rest and rotate right and jump and your usual stuff, jump equal, jump not equal, and so on. All those things are available, but they generally work on 64-bit addresses, 64-bit inputs. And you can look up the details to find out how they actually work. And as we're going to see, they don't all work exactly the way they should, which has been true in all other versions of the processor too. And it's true if you go to the ARM processor, not everything that you want is really there. And not everything works exactly the way you think it should. So here's the simplest one. It's just called write. We can send text to the console. We could send it to anything else because remember in Unix, everything is a handle and the same thing applies here. You have to specify the output. So first I set RIX to 1 to make it a write, and then I set RDI to 1, which is the standard descriptor 1 for standard out. That will write to the console. Then you push the string on the stack and set RSI to the stack pointer and call syscall. So you are also using the stack, but the only thing that enters the as an input is the register, which contains a pointer to the structure on the stack. So that's how it works. And now we can start writing programs. So I've got them ready to go. The only dirty trick I need to point out, which I just found out before class, is that you cannot install YASM on 64-bit Kali anymore with apt-get. They always break something with each version of Kali, and this time it is YASM is no longer in the repositories. That's the most common and least difficult thing to fix. I just wrote a version of that. In fact, let me just send it up to my server right away so I can point to it there. It's 127 projects. It should be the latest change. And that way I'll make sure it's available to everybody. Yes, this is a Java-based program, so you have to pause for a long time for it to do anything. Let's see if there's, my internet connection is, yeah, it's all right. There we are, 127 project. Okay, now these two things have to go up to my server, and then I should be able to point you to the new instructions to install ASIN, which are necessary for Kali. I did use Kali 2012. I imagine it's the same thing, 2013. All right, this is what I used to do. apt-get update and apt-get install YASM. That worked on older versions of Kali, but now you got to do this. And this, by the way, in case you're interested, in a package manager-based system like Debian, if they take it out of the repositories, all you have to do is go find the files that the previous one used, which are online, and you can download the raw deb package. Deb is the installer package that contains the binary code. So you go find whatever previous version before they took it out of the repositories and download the deb package, and then just do dpkg-i to install whatever's in the deb package. Yeah?
Like earlier this year, I did an APT update for colleagues.
Yeah.
I think it couldn't find the Berkeley server or something for a while. So
Right.
I had to VPN to the East Coast to get like the East Coast server.
Sure, that's a common problem. Just one repository will go down temporarily. But another problem, which is very big in Kali, is they take things out of the repositories completely, so they're just not there. And another thing that's common very common in all Debian-based things is that the version in the repository is really old, like 5 years old or more, so it's missing all the new features and bug fixes. So you often have to download newer versions from the package maintainer and maybe compile it yourself. And here, this is backporting, where you install something from an earlier version back when it was in a repository. And I don't know why they took it out. And by the way, this is kind of sloppy and unwise, because there may be a reason they took it out. Maybe it doesn't work or something, but most of the time, there doesn't seem to be. It seems to be fine to put it in. This is like taking a driver from, say, Windows XP and putting it in your Windows 7 box. Most of the time, you're fine, but you are, in principle, introducing bugs that some other person thought they better not introduce. So, you know, anyway.
So make install?
Make install is compiling from source, and that's probably a better general solution.
Right.
Because you might assume that they're build tools, but bringing in a binary from an earlier version that they removed is a pretty sleazy thing to do, but I do it a lot. It usually works. But you know, I'm an evil hacker. It's a virtual machine. I don't really care if I messed it up. Remember, she was here when I was doing an attack on the Mac. She said, "This is going to mess up my Mac." And I said, "Oh, I don't know." And she went, "Ugh." But you know, messing up your Mac is a whole different thing than messing up a Kali virtual machine, right? If I mess up a Kali virtual machine, it's half an hour lost. If I mess up my Mac, you know, I got pretty annoyed when someone messed up my Mac, actually. That's not fun. This guy had an anti-ransomware thing at the Cloudflare conference a couple of years ago, and it was a new kernel extension for your Mac. And he said, "Try this." So I tried it, and my Mac was dead. It wouldn't even boot up, and I'm like, hey, dude. He's like, "Oh, it's fine, there's nothing." It's nothing? Doesn't seem like nothing to me. So I took it to my best student here. He figured out how to get it back. Turns out if you had encryption on your hard drive, you're dead in the water. You have to get rid of the encryption, and now it'll boot up again. But I'm like, and I told him, he said, "Oh, I don't even need to put a note on the page or anything about that. That's not a problem." I'm like, "I think that's a problem. I'm not going to use any more of your stuff. I don't like your attitude." Anyway, but you know, so anyway, after you've done that, then you have the ability to do assembly. And so let me get the name of the thing here, ABC, right. So I've got them all ready here. And let me just pick a window and make it bigger. Okay, so let's see what I got. LS, oh, yeah, tell me it's broken, see if I care. Host is down. Host is down. Perhaps I brought up the wrong machine. No, all right, ifconfig. Perhaps it has a new address. It does, 172.16.1130. All right. I don't know why it's got a different address, but anyway. Right. Okay, DH, this should be not doing this nonsense to me. Let me see what happened. I'm in NAT mode. If I'm in NAT mode, you're not supposed to be doing this to me anymore. DH client minus V. There, now it's 142. Okay, I don't know what that other number was. There we are. Okay, so 127. Okay, this thing is called ABC. Oops. Or maybe it's called ABC1. That might be what I'm doing wrong. It is apparent. Okay, so we've been here before. We define a text section where instructions can go. We define a start, otherwise it would not know where to start running. And now we can execute machine language instructions after that label. So here, I just push A, B, C, D, E, F, G, H into a 64-bit register. So it's got enough for 8 bytes, which is 8 characters. Now I tell it the length of the string is, I just fill in the registers. So at first I push the string onto the stack. Then I move 8 into RDX, which is the length. I move RSP into RSI, which is the pointer to the string. And since I just pushed it on the stack, the RSP stack pointer points to it. And then I put 1 for the syscall 1 to write and 1 for the standard out to say where to write. So now when I execute syscall, it should print that string to the console. And then it's going to crash because I didn't exit. It's just going to run out of instructions before actually properly returning to the operating system. So to compile that thing, it's YASM down here. You use YASM minus F elf to make an object file out of it and then linker with LD, which I've already done here. But anyway, that's what you have to do each time, compile and then link. And then it is abc1.out. And there you go. It prints those letters and then it crashes. And the letters come out backwards because in 64-bit, just like in 32-bit, it's little endian. So letters go right to left, not left to right. So that's the simplest ABC. So let's fix the next one, which is ABC2. ABC2 is where we at least get it to stop crashing. So it's exactly the same up to here, and then we exit. So syscall 3C is exit, so you put that in RAX, and then do syscall again. Now it will exit properly instead of just crashing. So if you run that one, ABC2, it does the same thing. It prints this stuff. There's not even a carriage return at the end. It just prints it, and then it gets back without crashing. So that's the next step up. So the next thing you might want to do is put the letters actually in order. And there are probably clever ways to do this, but here's the simplest way to do it. Just put them in the other order, A, B, C, D, E, F, G, H, which is quite appropriate for us because we're going to be doing that with real addresses just like we have in other exploitations, so we might as well get used to that. And other than that, it's the same. So if you run that one, now it prints them in order, and there's no carriage return, and on it goes. So now we can do a little bit of stuff. Now we can do hello world, which is going to be hello. So if you go here, this is going to define a data section in addition to a text section. And in the data section, we're going to define bytes. And here we are. We put in that many bytes and then a byte of 10 at the end for the line feed. So we made a string in the data section, and it has a name. The name is string 1. So now when we want to push a pointer, instead of pushing RSP, moving RSP, we move the pointer to the word string 1 here. And that will put it there. Other than that, it's the same. Now it will print that stuff and then exit properly. And this is finally going to have the line feed at the end, so it will look prettier. So I can run that one. Now it prints hello world and press line feed, so that's nice. Now we can have variable length strings and terminators at the end and all that fancy stuff. So now we can try echo, which is going to be read.asn. So here, I define a placeholder to hold some room for spaces. So this reserves spaces for 10 characters in the data section. And I put in 4, 4, 2, and then one more, which leaves room for a null pointer. So I could put in up to 10 real letters and a null pointer at the end, and there's enough room for that. Now, down here, I'm going to do several syscalls. I'm going to do 3. First, I'm going to do read, then a write, and then an exit. The exit is simple, just like before, 3C exit syscall, nothing to it. This is the write, like before. I'm always going to print 10 bytes, take a pointer to the string and print it. This is no more different than what we did before, except before we only printed 8 bytes. And here's the reading. So I'm going to read up to 10 bytes. I pass the pointer to the string, but the pointer is used not to read the data, but where to put the data when it reads it. And syscall with an RAX of 0 is read. So it will read, and this is where it reads from to standard in. 0, 0 reads from the console, and 1, 1 writes to the console. This is, you may notice this is very, very close to C in and C out in C++, and fprintf and fscanf in C. And that's because, remember, the whole point of C is to have the simplest possible connection directly to machine code. C, that's why C is so dangerous. C, a line of C turns into just a couple of assembly coding instructions in the simplest possible way. You're almost writing assembly code when you write C. That's why it's so fast, and that's why it's so dangerous. Anyway, so this will read data from the input and then print it to the output. But it's always going to print 10 characters, and that's going to produce some screwy bugs. So when you run this one, which is read, okay, it wants to take some data, so I can put in ABC, and I get ABC, and then I get extra junk after that, because it always prints 10 characters, and it reserved space for them, so it's going to print stuff that's hanging around, left over from before. And remember, the first thing I loaded it with was, anyway, let's try that again. I think something funny when I moved the screen. Yeah, there was this extra stuff there. And when I moved the screen, it vanished. That stuff there is the stuff I put here. It's always going to be BBBBCC. So if I give it something else, like SAM, it's always going to have B's and C's down there. That's the extra stuff I left behind.
But you press enter, right? That's a character.
Yes, that's right. It took the enter I pressed and put it in as a character. Right, that's right. So it's put in 4 characters, SAM, enter, and now it printed SAM, enter, and that used up the A's. Then you had 4 B's and 2 C's. Quite right. So if I were to put in 10 characters and then enter, then it would lose the enter because it went too far. It only had enough room for the 10. And now it didn't have room for the enter. And I think that means I should be able to overflow it too. I'm not quite sure how much damage you can do with an overflow at this level, but apparently not so much. It just passed it back to the shell. But that's right. So that's what that one does. Now we can do a Caesar cipher. We can input data. It turns into stored numbers, and then we can output data so we can modify it. So Caesar is here, and this is where it's useful because it's going to show the problems. So now I have a data section, and I put in enough space for 8 characters. Then I read 8 characters. 0 reads from the input 0, which is fine. Now, before I print out 8 characters, which happens down here, I'm going to do some math. So what I do is I put RBX to a pointer to the string, and then move the string's value into RCX. Remember, 8 characters will fit in the registers. So I can put a whole string in one register. So RCX now contains all 8 bytes of input. Then I add this, 1, 1, 1, 1, 1, 1, 1, and then I put it back on the string, on the stack, per RBX points, and now I print that. So this should have incremented every byte by 1. So this is going to do Caesar cipher, where you move everything forward 1 letter in the alphabet. A will go to B, and B will go to C. One bug is Z is not going to wrap around and come back to A. It's just going to move up to a punctuation mark or something. So that's irritating, but you know, this is the first attempt. And by the way, of course, it's going to exit normally at the end. So if you run this one, /, yeah, okay. And now I give it, say, hello. The H goes to I, the E goes to F, the L goes to M, but the O doesn't change, and I have extra junk. So that's kind of disturbing. And on top of that, the carriage return that I entered stayed the same. It didn't increment to 11, which it logically should have, and that would, I'm not sure what that would be, form feed or something. So it doesn't seem to be working very well, and that's actually not obvious why it's not working very well. And the reason it's not working very well is actually pretty cruel. So to see it, let's use objdump to see what's in there. Objdump disassembles the file, among other things. If I go -D, it will do that. .out, Okay, so this is the real assembly language that was created by my assembler. And notice something. There's a point where I added, this is my entire text section. So here I am putting 8 in RDX. It's in this way and this way. Notice this is the other notation where it's sourced to the destination here. Then I call Syscall. This is what 0, 0. This is what reads from the input. Then I put the pointer to the data section here in RBX, and here's the add command. Notice how that compares to what we wanted to do. It adds 0, 0, 0, and 0, 1, and a 0, 1 where it's dropped to 0. It only adds 4 bytes of 1, not 8. So I told it to do something else. If I look at my input, this is Caesar.as, I told it to do that. But it really did that. Now that is rude. It didn't pop up an error message, as I recall. I don't believe seeing one. Let's try compiling it again. I didn't compile it right in front of you. Let's go back to assembling it and see if it warns me at any point that something is wrong with this code. I think it will. Yep, warning. Value does not fit in 32-bit field. So it told me, if I paid attention to the warnings, that my program was not compiling correctly. And the reason it happened is shown up here. If you go and look up the Intel add page and see what adds are available, what I attempted to do was to add something to a register. And you might think you can add anything to a register, but that is not true. If you look through here, you've got add a register to immediate 8, immediate 16, and immediate 32, and add a 64-bit register with an immediate 32-bit value, but there is no add 64-bit to an immediate 64-bit. I don't know why, but it's not available. So you cannot do it in one instruction here. So that's pretty annoying. So you have to do it in 2 steps, which is when we get into ARM, you have to get used to this, everything is multiple steps. You can't do anything except in registers. So you always have to.
So these are like half-baked 64-bit in a way.
Well, you could argue that. Yes, it's certainly not as simple as every 64-bit instruction that you might think should be there. That's not what any processor does. No processor is like a mathematical list of every possible instruction. They give you certain instructions which are enough to get anything you want done, but often you have to combine 2 or 3 of them to get something which you might imagine should all be in one instruction. And in ARM, that is almost always the case. You can't do anything except the registers. So your typical data flow is first, take the registers and save them somewhere, put whatever you want to work within the registers, work on it in the registers, put it back where you put it, and now bring back what you stored.
Was the IA-64, was that like an actual 64-bit?
Yeah, it's a real 64. This is the real Intel 64-bit. This is the way it really is. And this is the way every processor always has been. They don't have every command you might want. They have whatever they decide is enough. And you might have to combine several commands to get what you think ought to be in one command. And when I started in the world of 8-bit, I frequently wrote self-modifying code to make what I wanted happen. But you know, they're all NP complete in that you can get anything done, but it might take several instructions. So the modified Caesar is here. Did I call it Caesar 2? Maybe I called it something else. Called it Caesar. Yeah, Caesar 2. Okay. Let me check. I thought I had it. Apparently not. All right. Let me put it in here. So all I have to do is change this line to this. So let me do that. Okay, let's copy Caesar 1.assemble to Caesar 2 and nano. All right, and this is the offending instruction. So let's put in that stuff instead. Okay, now instead of trying to do it in one command, I put this number in R8 and then add R8 to it. So hopefully there was nothing important in R8. Since I'm writing this code and it's very small, I happen to know there's nothing important in R8. Otherwise, I might have to first store R8 somewhere, then do this, then restore R8 from where I stored it. So if I do that instead and compile that with this stuff, Now, if I put in hello, it does IFMMP. So it does add to that. And I think this is probably an 11 instead of a 10, but it's not easy to tell. I don't know what an 11 is. Anyway, that's the point. Now it does what it should do because I used a register to get the correct 64-bit processing. So there's that to do, and then there are some challenges where you have to write some modifications of this. And the last thing I want to do is talk about good old assembly, good old buffer overflows. So let's do a 64-bit buffer overflow. We'll find it there, of course, it's very much like a 32-bit buffer overflow. There are only a few changes. There's a comment coming in. Might have warned you about the encryption in advance. Encryption?
Talking about the story you told at the beginning about your Mac.
Oh, well, yes, that was my feeling. Yes, he might have. He didn't know it, and he didn't even care. Anyway, so the part of me, I can't entirely fault him for not knowing, but not even caring and putting a note on your web page, don't use this if you have encryption, that really bothered me. Anyway, so, all right. So let's see, I've got this thing. I think I called it vulnerable or something. Let's see, I called it P13, okay? So let's cat P13.c. And there it is. You include the usual stuff. The C code is quite the same. The only thing obviously different about C code is I decided to just print out the RSP here for no particular reason, just so you could see it. And perhaps so you might notice if you're actually on the left address space layout randomization on. So this will just read an input and then return from it. But it's going to read up to 800 characters and you only reserve space for 400. So if you run that, that is P13.c, and you put in some stuff, it comes back and that's fine. So I'm going to need to put in something long to crash it. So I wrote this fuzz program, which prints 450 eggs. And so if I run that and put it in a file called F, and then do ls-l, I can see that the F has 451 characters because there's a carriage return at the end. So if I run that, P13, and get the input from F, it crashes. So 400 is the amount of space I reserved, and 450 is enough to overwrite the control characters until I corrupt some essential byte and cause it to crash. In 32-bit assembler, the thing I would hit would be the EIP. As we're going to see, that is not what happens in 64-bit assembler, not quite as simply, because of the dead zone in the middle is going to get us. So we got to try looking at this GDB, P13, and then run, you take the input from F and let it crash. And when it crashes, it ends up with this value in the EIP. Remember, that's what it prints right there. And I expected this to be AAAA, and it's not. And the reason it's not, if you do info registers, you'll see an AAAA here in the RBP, but not in the RIP. Now, the reason this happened, you can see if you view the exact instructions that crashed. But let's do it with a breakpoint. So I'll disassemble Bowne, as we've done before. And remember, you can read this pretty easily. This is what prints something. This is what prints something. This is what reads something. That is where the overflow happens. It reads input from the user, and the input is bigger than it should be. So I would like to break before and after this point. So let's break at Bowne plus 64, and then we'll let it crash after that. So break at Bowne plus 64. Okay, and now run it again. Run from F. Yes. Now this is before it crashed. So now, if I do info registers, I used more precise commands in the instruction because this is kind of messy now in 64-bit because there's a lot of registers. But you can still find RBP and RSP, our old friends. So it goes from 350 to 4F0. So this is the base pointer, 4F0. So I can X RSP, and I'm looking for 450, 4F0 as the bottom of the stack. So I'm not there yet. I have to press enter. And here's 4F0. Now you have to think bigger. It's the 64-bit word starting at 4F0, which is this. That is the stack frame. This is the stored int return value. And notice it's all full of zeros because all the user code is in the lower segment of that split memory. All the addresses allowed down there start with a bunch of zeros. So this is the return value, 405FA. And this is before the overrun. Now, if I just continue, let's, can I continue? I think I accidentally quit. Okay, let's just run it again. Doesn't matter. Run it. Now, yes. Now continue. I want to let it crash. And when it crashes at this point. And if I examine the stack again, which I'm going to do by saying, I want to see, remember it was 4F0. It was this thing here, which was my return value. So let's take a look at the stack here. So I think I'll just dump it from this point. That will do. So x/64x from there. Okay, so here's the 41s and 41s. I do have 41s on the stored return pointer. Okay, I did overflow the stack. I did overflow the return pointer, but it never ended up in RIP. And the reason is because of the code it was trying to execute. It wasn't able to get that far. So we should be able to see that by doing this, x3i. Let's take a look at the commands that actually crashed. Examine 3 instructions at the instruction pointer. And you'll see, here's the command that crashed, retq. Now, retq is the end of a routine when it's returning to the host above it. And what it's doing, the last thing it does before returning is it pops EBP and restores EBP to its previous value to move you back into the other stack frame. And the problem is, when it pops EBP, it is popping this value. And in our 32-bit buffer overflow exploit, you may not remember way back in project 2 or 3, we made the first buffer overflow exploit, and we said, you can get it to run some code, but it will then crash because we broke EBP. Because as you're filling the stack, overflowing stuff, first you overwrite the stored EBP, and then you overwrite the stored EIP. And in a 32-bit register, you can fill the EBP with garbage, and it doesn't crash right away. It goes back to the calling routine, and then it will crash later when it tries to use EBP. But in 64-bit code, it will crash at this point because that is not a legal value for EBP, because EBP must point to the stack. And the stack cannot be pointing to the middle of address space like this. It can only allowed to point to addresses that start with a bunch of zeros or with a bunch of 7FFs way at the top. So it will not make it far enough to use this instruction we implanted if you put a stupid value here for EBP. So that's the only wrinkle about 64-bit exploits.
That's the only difference to make it work?
Yes, that's the only real problem. Other than that, it all works the same. So now we can make a real exploit. So we make a finder, which is slightly different than the fuzzer. And I think I'll just open another window here. All right, this one seems to still be connected. That's fine. So let's nano find there. So all this does, escape Y, okay. All this does is the same thing we've done before. You print 350 A's, and then you print 50 pairs of numbers. So it's a total of 450 characters, but the last numbers keep changing so I can find things. So if I run that, which is find, it's this, the same total length, but I put a non-repeating pattern of numbers at the end so I can tell which ones are hitting. And now I feed that in instead of my original. So I put that in F, find into F. And now in my assembler, I go run it again. And I continue. And once again, it crashes. And I didn't hit this value, but I can see what made it an EBP with info registers. And RBP is now this, 33.
Looks like numbers?
Yes, 3. So what I expected actually was, that's right, that's what went here, but I really want to see the stack pointer after that. So this is 33 and all that jazz, but this one here should be a little different. So I can do that by examining my stack, which was this. I had a nice stack finder, and that one, wasn't it? Yeah, it was this one there. And so there's the stored base pointer, RBP, and this is the stored EIP, RIP. That is my instruction pointer. And you can see this is 3940. You omit the 3 and read only next number. 33 is 3, 39 is 9, 40, this is 3738. So maybe this is getting a little screwy, but this is the way 64-bit text goes. It starts here and goes to the left, and then continues here and goes to the left. So this is the string 37, 38, 39, 40. That's what ended up in, that's what would end up in the instruction pointer if I put something valid here. So that gets me to here. That's what I have, 37, 38, 39, 40. And so now I can form an attack file. And I think I've got this one ready to go. Yeah. So this one here just goes up to padding. I figured out it was 424. And I'm going to put in a dummy exploit now. 190s for an op sled, 200 cc's, room for my shell, and then padding to bring it up to the right length, and then the RIP, which will be A, B, C, D, E, F, G, H, trying to make sure I'm hitting it. So that attack, if I chmod plus X, attack, and then I run that, that's going to print that kind of junk. And if I put it in F, it's going to do that. And I should now be able to see it here. So if I run that, and then continue, and then check my stack, I should see here A, B, C, D, E, F, G, H. So now I can target the RIP. And all I have to, I can put an address in there, and I choose an address that is in my NOP sled.
But how did you figure out the 420 or
the what? Oh, the 420? Oh, because I could see where it was in the pattern of stuff. So if you go up here, it was here, 39, 37, 38, 39, 40. And so if you look at my script, there, it's right here, 37, 38, 39, 40. Oh, so I just took how much of that there is, and it turns out that's, right. This was 350, and this was 70 more. So it was 420 before that. Okay. That's why you do this. This lets you pinpoint.
Yeah, I usually do like binary search. I go like 500, I go 1,000.
Oh, you can do that, but this is what most people actually do, and there's even there's even a Metasploit module to make these non-repeating strings. I always just write my own because Python loops are simple, but you can, there's a module people like to use that makes repeating strings. Okay. Non-repeating groups of 4 characters. Yeah, that's a common step. Okay, so now the next, I need to find my NOP sled. So let me get to follow my instructions. There's my NOP sled. So to find it, I got to look a little higher. This is my EIP. So let's look up, let's see what it is. E43, let's try E3 and see what happens. Okay, there's my C's, but I just missed the NOPs. So let's go to 2. There's my NOP sled. Okay, so any of those addresses would do as an address to put in. So there's one. And what I usually do is copy it and then put it in my exploit file. So let's copy attack 1 to attack 2, nano attack 2. And I'm just going to put this someplace there. So there's my NOPs. So logically, that would be the number I want to put here, which is 70 E3 F F F, then 7F. See if that's right. It's pretty easy to get it wrong. 1, 2, 3, 4, 5, 6. That doesn't seem long enough at all.
Quotation mark.
1, 2, 3, 4, 5, 6. Apparently 6 is correct, and you're right about the quotation mark. Let me check my instructions here. I'm a little bothered by the zeros that are missing, but I think that's all right because this is at the end of the exploit. So let me check my, okay, here's what I did. Right, logically there should be 2 zeros at the end, but there's really no point even putting them in because the first one will terminate. But anyway, let's put them in. They don't hurt anything. It's just that they won't actually get passed beyond to the program from the processing. Anyway, so now NOP-SLED plus BUD plus PAF plus RIP, that looks good. And now if I run this one, I should be able to see that the right value is in there. And it will make it to that point. All right. Now, the one thing that confuses me is why didn't it crash at loading the EEP 5858? This part I don't remember, and let me see if I can understand it. Oh, I think I've been saying it wrong. It doesn't crash when by putting the RBP equal to that. It tries to put that value in the RIP, and it fails because that value is not a legal value for the RIP. So it's getting to the right instruction, but then it's not finishing it. What happens in 32-bit is it loads the value in the RIP, and then it tries to jump to the RIP, and it crashes at that point. So that's what's going on. It's not the RBP, it's the RIP. But it refuses to even put that value in the RIP because it's stupid. Now I put a valid value in the RIP. So that's better. And let's try this one. So attack 2, a chmod. Attack 2. And then attack 2 to F. And now, whoa, that's interesting. Okay, I followed it up. Okay, I got too many quotes. All right, let's try that. Okay, let's do an ls minus L for good measure. 433, that's believable because it was 450, and then I skipped a few at the end. So now let's run that, and yes, and continue. And this is good. It now hit a CC. And so this is somewhere in my NOP-SLED. So it worked. I was able to feed in the RIP and jump back to my NOP-SLED. So I could now just add any Metasploit payload there, and it would run. So I've got control of the machine, and that's the essential part that's different. And now you could just make shellcode and inject it, and I don't think I'll bother with that. That's the same as before. You just use an MSF Venom, except, of course, you've got to make 64-bit shellcode. Remember, the one thing irritating about Linux is it does not run 32-bit code on a 64-bit platform the way Windows does. You can add optional libraries to make that possible, but by default, it does not, because Linux is not concerned with backward compatibility the way Windows is. Anyway.
Is there any like bad characters like X20?
Any what?
Bad characters?
Oh, there very likely are. And in fact, the 0 is a bad character, so I managed that second 0 I put in there is never going to get there.
Like 9, 10, and 20?
You never know. It depends on the program you're talking to. You'd have to look at your C code. But if you just input, like from the console, then it is usually just 0. But if you pass through some other stages of processing that try to parse the arguments into segments, then often separators matter, like spaces and tabs and such. That's why you have to look at the code that's processing. But in this simple case, I think it'll be just null. But that's, of course, a good point. Anyway, then you've got a complete attack scripter, and you can make a root shell. So here I made a listening shell. All right. And I think that's it. Let me go take a look at my slides and see if there's anything missing. I think the slides just step through this. Yeah, we did that. The letter's in order. Yeah, I think we've done all of this stuff. And so for the projects, you've got the assembler here, and then the buffer overflow exploit here. And then you've got extra credit assembly challenges down here. And I think that's all for the 32-bit. The other thing, which I just got to add this semester, is the ARM stuff, which we'll get to. If you are done absorbing the difference between 32 and 64, you might as well go to ARM, because Intel 64 is going the way of the dodo bird. Everybody has already announced they've had it with Intel. Intel wastes too much power. Everybody's going to ARM. The Macs are going to ARM, and the servers are going to ARM. And I would think it won't be too long before the desktop PCs will go to ARM. So this Intel stuff is on the way out, and we ought to start looking around the corner.
Well, I think there's no competition with Intel. That's the problem. Like, we stuck on block code for how long on the super level?
Well, sure, that's an issue. Although I've seen them announce there's one coming out that's going to have like 18 cores. Or,
right.
Yeah, but you know.
That's because of AMD more cores.
It is, but AMD is compatible with Intel. So if AMD was to win, we wouldn't go to ARM. But apparently ARM is better because it uses less power. And that is turning out to be the most important issue in modern economics. So what people say is a lot of them are jumping to ARM. Anyway, even if Microsoft or PCs don't move to ARM and Macs and servers do, that just means we need to know both of them. And it's all very similar. So it turns out it's pretty easy to use websites that will let you process ARM. And so it's good to see a little bit of difference, especially in the Internet of Things. You're going to just have a lot of hardware, like Raspberry Pis and everything, and a lot of it's running ARM or even something else. So you have to sort of get used to minor variations in the.
And the security in the IoTs are bad.
It is. The IoT is a very good place for security researchers and workers because there's no security now. So even very simple measures to improve the security are very good. You don't need to be a genius to improve it. Yeah. All right. Any questions on anything? Because I think that's about it. I will stop the share. I didn't have any iClickers today. I guess I'll see you folks next week. Let me check the schedule. I don't think there's a holiday or anything, but sometimes I miss these things. It was right there. I tried to go back to the wrong page. This here is October 13. Yeah, so next week we'll be here, and it'll be at 1 p.m. again. There is no contest next week. There'll be another one coming up, but probably not for about a month.
So this is going to be a permanent use.
This will be the permanent room, I think, because I like to leave that room down there for the club. They've been having too many people to fit in the little hacking lab. So we might as well take this. There's room for both of us on Saturday. All right. Good.
So a lot of Windows from now on?